that has a 0 radius, and then we just start letting it grow, all right? So it's almost like, imagine on the ground, like let's say we take I don't know, some oil or something, and start pouring it into a puddle, and it starts growing on the ground, right? Then, if the radius is growing at a certain rate, I could start asking, look, at an instant in time, how fast was the area growing? How fast was the area changing at the instant that the radius was a certain radius? Yeah? Okay. And to do that, I'm going to need to take a derivative of that, right? All right, so that's what our first example is going to be. So let me bring up the notes for this. And then we'll get back to this circle, all right? Just keep in mind, related rates. Think of the name of the section. Related rates. Okay, so the PV equals nRT, right? That pressure volume equals nR temperature, right? When I asked you to find those derivatives, the equations you had related the rates of things together. It was like dV dt is equal to this, and it had like dP dV, which is another rate. So you had a rate on one side and a rate on the other side. They were somehow related to one another. Related rates. Okay, that's what it's about. Come here. Now, I don't want to read all of this, but it says we've reached one of the most exciting sections in the class. We now study applications of related rate problems. It's one of the most challenging sections of the course. Students often struggle with this section because it involves word problems. I admit these are intimidating at first. I assure you that there is a systematic approach to these problems, and once you figure out how to translate the given information into mathematics, you might just come to enjoy this a little bit. As you'll see, there's an expectation here for you to know some geometry, trigonometry, basic formulas, areas, volumes, etc. So I do have an expectation right now that you know the area of a circle, that you know the area of a triangle, that you know circumference of a rectangle, that you know, there's a lot of different things that you're going to need to know. Or you're going to need to know where to get them. And on your formula sheet, there are formulas there for like, does anyone here know the area of a sphere? Or is that volume? Okay, so on your formula sheets, there is one page that has geometry. I think you got it out there, sir. What page on the top does it say that is? Reference page what? Page 1. Page 1. So it's got some common three-dimensional objects there, sphere, cylinder, and a cone. And there are formulas for area, surface area, and volume. All right, so just be aware that that's where they are. But there are other things that you need to know. You need to know similar triangles. But we'll get to it as we get there, okay? Don't hesitate to Google a formula if you don't know it, okay? If you're at home trying to work something out, use Google. All right, we will begin slowly and work our way into more and more involved problems. And so, is there a procedure? I say here, there is not a cookie cutter way to do every problem, all right? But there are some things you could do that you should try and follow when you do these problems. It might help you. And here's what I have for the steps. And giving you the steps now without giving you an example doesn't really help, but let's just talk about this. We're going to be drawing some pictures of an exact moment in time, because all of the problems we're going to be doing are going to be problems where things are changing. So instead of me giving you a circle, the circle is going to be growing. Or instead of me giving you a triangle, the triangle is going to be growing. So everything's going to be in motion. One picture you're going to draw is going to be a snapshot, like you're taking a picture of that situation at a specific moment. The other picture, second picture you're going to draw, is going to basically let everything move. And so you can't fix any particular sides or anything like that because everything's in motion. So you have to assign variables to those sides. After you assign all your variables, you determine any rates or constants, then what you're going to do is somehow find an equation which relates what you were given to what you're trying to find. That's one of the key elements of the problem, as you'll see. We need to come up with that equation. So like PV equals nRT or area equals pi r squared, we have to come up with that equation. That's never going to be given to us. And then we're going to use implicit differentiation and differentiate the equation that we came up with, and then we're going to plug in all our information to solve. It's like we plug in the x and the y to find the slope of the tangent line. We're going to plug in all the things we know to figure out the answer. All right. Let's say we have a circle. Ignore all that. Here it is. Here's a circle. Now I've written this program in a specific way. This is an expanding circle. The radius is increasing at a constant rate. So it's almost like someone is standing here. You got, let's say, the center of the circle. I've got like a rope, and I'm pulling from the center of the circle. I'm pulling the radius out. So just imagine the circle gets bigger as I pull the radius, but I'm pulling that radius out from the center at a constant rate. I'm not speeding up or slowing down how fast the radius is changing. Then the area is going to change, isn't it? And I've written the program so that when I press play here, it's going to start drawing this circle, and that radius is growing at a constant rate. All right, so if you imagine the distance from here to the edge, that is increasing at a constant rate. All right, this right here is moving at a constant rate. But I want you to pay attention here to the radius. You can see that if you count it out, 5, 6, okay, here we go. 1, 2, 3, right? Sorry, 4. Like that's a constant rate that I'm counting at. But look at the area. 1, 2, 3, 4, 5, 6, 7, 8. See how it's getting faster and faster? So as the radius increases at a constant rate, the area is not increasing at a constant rate. It's accelerating. It's actually getting faster. And so what we want to do here is we want to say, look, at some instant in time, let's say right there, at that instant, how fast was the area changing? At that exact instant. So it's like if I just take a little infinitesimal change in radius, if I just go change that radius just by a little infinitesimal, how much will the area change by? Make sense?
Yeah, there's a ratio that will tell you that.
That's right. So we need to figure it out. What is it? All right? Understand? All right, so I need to actually state the problem. Here we go. Here's the problem the way it would appear. If the radius of a circle is increasing at a constant rate of 0.5 feet per second. This is feet over seconds, so feet per second. Then how fast is its area increasing when the radius is 4 feet? So you've got this circle, it's growing, right? Half a foot a second. That's how fast the radius is growing. At exactly the moment that the radius is 4 feet, snap the picture, how fast was the area changing at that instant? Okay? Understand it? Okay, I'm going to draw 2 pictures to start this. I'm going to have what I like to refer to as my general picture, and the other one is going to be the moment, or the exact moment in time. And let me try and explain to you why you have to have 2 pictures, all right? Because this is important. Let's say right now, how fast am I running? Right at this instant, how fast am I running?
You're not.
I'm not, right? I'm not. I'm not moving, so I don't have any change in my speed at all, or there's no speed here, right? Now, same situation. I'm running. Right, see, right when I was there, right? At that moment, I wanted to be able to figure out how fast I was running. So the general picture, you're going to be basically letting everything move. And then in the exact moment was someone taking that snapshot of me at that specific moment. Does that make sense?
Yes.
You cannot talk about how fast something is moving if you fix everything. If I set my radius to 4, this circle's not growing anymore, right? So it's impossible for me to tell you how fast the area is growing if I fix the radius at 4. Now, when I take my picture, the radius is 4, but in general, it's not. Make sense? So my general picture, I'm going to use this dot to my advantage here. My general picture is a circle that is growing, and therefore I'm going to call this R, and I'm not going to fix it. And then in the exact moment picture, I'm going to take that same circle, and yes, I will fix the radius to be 4 here, because that's when I took the picture, right? So that's kind of like my snapshot. So I've got kind of a general picture, the exact moment in time, and now I'm going to write down 2 other things. I'm going to write down the information that I'm given, and I'm going to write down the information of what I want. What I'm given and what I want. Somewhere in this problem, that's weird. I don't know why that looks weird to me. I just noticed that. Does it look weird to you, like the distance from this board to the bottom of that picture, or to the bottom of the projector? Like this looks like it's parallel, doesn't it? But then up here, this line right here doesn't look parallel to my text. I don't. Okay, never mind. It's bothering me. It seems like the whole screen should be turned that way a little bit, right? But then that would make this look different. So I think it's skewed because it's coming from an angle. All right. All right, what are we given? So tell me what we're given, or if you want, tell me what I want. It doesn't tell, and you can't, don't cheat, no cheating, Diego. You have to wait. Okay, so. Well, let's read it. If the radius is blah, 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 what is this?
You want to know one something.
That's the rate. That's a rate, isn't it? Now, why is it a rate? Feet per second. Feet per second. Miles per hour, right? That's a speed. Speeds are rates. Speeds are derivatives, right? We've talked about this. The derivative of something is the speed of it, the rate at which it's changing. So this is a rate. This is the rate at which something is changing. That's the rate at which what is changing?
The growth of the circle.
The what?
Area.
Nope.
The
Radius, right? Look at, so it says the radius is increasing at a constant rate of that, right? That means my radius is changing with respect to time, isn't it? So dr dt is 0.5 feet per second. I am given that information. I am given a derivative, aren't I? The rate at which the radius is changing. I used r here. Why? Because that's what, in my picture, I called it r, right? The radius was r. So I'm saying that variable r is changing, and I used little t here to represent time. And where do I get the idea of time from? Feet per second. So I'm going to use radius with respect to time. Make sense? All right. That means in this problem, I will be differentiating with respect to time. I have automatically fixed myself into that because t is down here. Everything will be differentiated with respect to time. All right, that's what I'm given. What else am I given? Or you know what? Let me ask you, what do you want? You don't have to do any of these in any order. You can do this first, this, mix and match, plug and play as you go. Do you know what you want? How fast the area is changing with respect to time. So I want dA dt, don't I? That's what I want. But I want that when? At what's 4 feet? At r equals 4 feet. Okay. I know the radius is growing at 0.5 feet per second. I want to know how fast the area is changing at exactly the moment that the radius is 4 feet. Yes? But I know I can't plug 4 into my formula because that will fix everything, right? I think we have enough. We have enough to get started. So I'm going to bring up my notes again. Well, my notes said here that if you're doing these like steps, you know, that you want to draw some pictures, assign variables, write down what you're given and what you want, and then you have to find the equation. That was the next thing. Find the equation. And the equation that I'm talking about is the equation that somehow connects this variable here to this variable here. Why in the world would I want to have an equation that has A and R connected? Why?
If it wasn't, it wouldn't be called related rates.
Yes, that's true, but why am I not using, think about this. You're trying to come up with an equation that has A in it and R in it, right?
Yep.
Why?
Because you're
Well, I know I'm given A and I'm given R, but you're not always going to be given what you...
You're looking for a set value of R, and you're looking for A, so one variable, one given.
Hold on, back up. If you have an equation that has A and R in it, and you differentiate it with respect to time, what must pop out of that? dA dt, right? And dr dt must come out somewhere, right? It has to. It has to. And if that's that, I'm given a piece of that, right? And I want one of those. So my equation should connect these two together. Now there might be some other crap in the equation that I don't like, but I got to come up with any equation that relates the area of a circle to its radius, right? That way I can guarantee these two different derivatives will pop out when I differentiate it. All right, so I'm going to come up with the equation. The equation I'm going to use, obviously we've already talked about this, is that the area of a circle is pi r squared, right? I've got my A in here, that'll take care of this. I've got my R in here, that'll take care of that. So now it's time to differentiate. That's the next step. I'm running out of room. I'll put it down here. Next step, I take the derivative with respect to time of the equation. Now, I normally didn't write this, but I'm writing it now because I just want to stress to everyone that I'm differentiating with respect to time. I'm doing that because that was what my given information was, and that's what I want. I just took this equation, derivative with respect to time on both sides. So, left side, what is the derivative of A with respect to t, or time? dA dt. Am I happy to see that? Yes. Absolutely, because that's what I'm trying to solve for. So I have dA dt on the left side. Now, on the right side, I have pi r squared, and I'm differentiating with respect to time. Pi is a constant. It's going to come for the ride. All right, so pi is coming down here. And now I need to take derivative of r squared with respect to t. 2r, right? First power rule. 2 comes out. 2 times r. Then chain rule says take derivative of what's down there, which is dr dt. There it is.
Well, isn't that the circumference formula without the dRdt?
Yeah, that would be circumference, but that's, I'm not sure that that's, it's just kind of a cool result. It's not really connected to it. I mean, I guess you could say that the area changes by the circumference times the rate at which, I mean, you could say that, but it's not something that we need for this. All right, so this is it. Let me squeeze that in. Let me squeeze it in right up. Well, I'll put it right here. So here's what I know. dA dt is equal to 2 pi r dr dt. This is it. This is it. This is the formula that we're going to use. Now, at this point, after we have taken the derivative, you are allowed to plug everything in. This is you actually now taking that snapshot and figuring out what the answer is. So, in order to figure out how fast the area is changing with respect to time, which is what I wanted, I need to know the radius at that instant in time. Do I know the radius at that instant in time? It's 4, right? Do I know how fast the radius is changing with respect to time?
Yes.
Yes, it's 0.5.
Yes.
So this is just going to become, I'll put here, so, I have to erase. I'm sorry, I have to erase. So, dr, or dA dt, will be equal to 2 times pi times 4 times, I'm going to put 1/2 instead of 0.5. Now notice I did not put any of the units here. I didn't put like 4 feet. I didn't put 1/2 feet per second. You can put those in there and then like figure out what your units are, but I do it a little different. This is equal to what? 4 pi? 4 pi. But then the answer, you must give me the units. So square feet, why is it square feet? All you have to do is come back here and look at this. How is area measured? And your units are always squared, aren't they? And how is time measured in this problem? Seconds. So you don't have to put the 4 feet here and then the feet per second here. You can just look at this part right here and figure out what your units are. This is going to be feet squared per second. So you put here feet squared per second. Which is approximately, what's 4 times pi? Approximately. It's about, well, do it on your calculator. What do you got? 12.5, 12.6-ish square feet per second. All right? Well, that's the exact answer. I want the exact answer. 4 pi square feet per second. But that's the approximation, 12.6. Y'all good? All right, I want to go back to what I put on the board when we first started this problem. We made a little table, didn't we? We made a little table, and we had R was 4, and the area was 16 pi. And then if R was 5, it was 25 pi. And the difference between those was 9 pi, right? So if my radius jumped up by 1, the area jumped up by 9 pi, right? This, though, is not telling me how fast that radius was jumping, all right? This is a completely different picture. I want you to see that. This is a completely different situation. When I was doing this, I was just trying to get you to see that it's not jumping up at a constant rate. So it's growing faster. This is saying at exactly this moment that the radius was 4. If that radius was growing at that rate of 1/2 foot a second, then the area would be exactly increasing at 4 pi square feet per second at that moment. All right? I think we should try another one. How are we doing on time? 15 minutes? Yeah. Y'all seem like y'all are ready for something a little more involved. Not that involved. Not that involved. Yeah, no, I'm going to save that for...
Don't give us the hot stuff yet.
That stuff is like steaming hot. I don't like it.
All right. How about this one? This is a sphere this time. Okay? So we have a sphere whose radius is changing at a constant rate. It's a sphere. It's hard to see that. It's three-dimensional, but okay? Your sphere, if the radius of a sphere is increasing at a constant rate of 2 feet per second, How fast is the volume increasing when the volume is 3 pi cubic feet? Or 36 pi cubic feet. All right. Read the problem. If the radius of a sphere, so we have a sphere, three-dimensional.
Yes.
It's increasing, it's growing. That radius is increasing at 2 feet per second. How fast is the volume increasing? Because we're three-dimensional now, this is volume, not area, right? How fast is it increasing when the volume is 36 pi cubic feet? All right, let's start with some pictures. General picture, and then the moment in time. All right, we need to draw a sphere. So you can draw a circle, and then you draw kind of like an ellipse, like this, and then put a little dot in the middle, and that kind of looks like a sphere. That sphere has a radius, which I'm going to call r. Then I have a specific moment in time where I take my snapshot. And what can you tell me about that moment in time? This is tricky. It's a little different than the last problem. The volume is 36 pi cubic feet. That's all I know about this moment in time. I don't know the radius, do I? What I know is that at this moment, the volume is 36 pi cubic feet. Okay? That's what I know. You okay with that? But tell me, is this radius fixed right here? Yes. In this moment in time, this radius is fixed. I just don't quite know what it is yet. I'm going to have to work it out. All right, let's write down what we're given and maybe what we want. So what are we given in the problem? The rate at which the what is changing? Radius. So dr dt is what I heard. Dr dt is 2 feet per second. And what do you want? dv dt. How fast? How fast you're thinking derivative? How fast is the volume? Oh, the derivative of the volume is what I'm thinking. How fast is that increasing when the volume is this? So I want dv dt at exactly the moment what? What's 36 pi? At exactly the moment that the volume is 36 pi cubic feet. That's what I want. Yes? All right. What's next? Find an equation that relates the radius of a sphere to the volume of a sphere. And so you go looking through your formulas, and you figure out that there is an equation for that. And it is? You have it. You have it. The equation is volume equals
4/3 pi r cubed.
4/3 pi r cubed. But were you talking about? I thought we were talking about area.
Oh, surface area of it?
I said, because I think I asked, do you all know what the surface area or the area of a sphere is?
The area of a sphere?
That's not what we're using here.
I know.
Yes. 4 pi r squared?
Yeah.
4 pi r squared.
You don't have to say surface area, not just area.
No. Well, no, you don't have to say surface area. I think it's understood.
Semantic.
Yeah. All right, so this is our formula, right? This is what we're given. So now what? Take derivative with respect to time. Take derivative with respect to time. So I'm going to go back to this, okay? Just understand I'm taking derivative with respect to time. So what is the derivative of v with respect to time? dv dt. Am I happy to see that?
Yes.
Yes, I am. Equals 4/3 pi, all a constant. Right? That's all a constant. So it's coming along for the ride. And now I need to take derivative of r cubed. Chain rule first, right? So 3 r squared. And then the very important thing that pops out here, dr dt. And I'm happy to see that too, because that's part of what I was given. You see what I mean by why you need to come up with an equation that has both v and r in it now? I mean, like, when you differentiate it, the things are going to be there, right? Notice that these have not turned into 1 ever, right? Like, none of these were 1. And it was because we're differentiating with respect to time. And unless time is in here, like in our equation, we're never going to have any of them go to 1. All right. We're there. So, dv dt, which is what I wanted, is equal to, now let's clean this up. The 3's cancel here. In order to figure out what's going on, I need to know, well, 4 pi is constant. I need to know what the radius is at this snapshot picture in time. And I never gave you the radius. I only gave you what? The volume at that picture in time. So now what I'm going to do is I'm going to come back over to this picture, and I'm actually going to rewrite this as 4/3 pi r squared equals 36 pi. See, because isn't that what volume is? If I tell you that the volume was 36 pi, that means that 4/3 pi r squared was 36 pi. Do y'all follow me? And I can solve this for r. Solve that for r. So how would you solve that for r? Yep, you can, let's kill the pi's off. You can just divide pi out on both sides.
Wasn't it cubed?
Oh, was it cubed? Ooh. Sorry. See, you got me thinking area. All right. There you go. 4/3 pi r cubed. Cancel out the pi's. And then I'm going to divide both sides by 4. Because that gives me a nice number over there, right? 9. So I have 1/3 r cubed equals 9. You can do this any way you want, all right? I heard multiply both sides by 3. You could have done that. I'm going to do that now because it's just an easier number to work with. So r cubed is 27. Cube root of 27 is 3. So my radius is 3. Do y'all see how I did that? Okay. It would have been nice if it said, hey, how fast is the volume increasing when the radius is 3? But that's not the way it was given. It wanted to know at exactly a moment the volume was a certain volume. So we had to go back and recover the radius. And then we can come back over here and we can now put that in for that r. Y'all good? Okay, so I'm going to rewrite this. This is 4 pi r squared, which is going to be 3 squared times dr dt, 2. And yeah, this r, remember, you cannot plug the r in here. Right? Why couldn't I do this, get my equation, and then go back, get what r is, and plug 3 in right here? Why can't I do that? Why can I not plug r in right here at this point? Because if I say volume is equal to, and I plug r in here, this is going to be a constant, isn't it? And then when you differentiate both sides, you're going to get dv dt equals derivative of a constant, which is going to be 0. And that's when I asked you, how fast am I running?
0.
0, right? I had to actually run and then tell you, like right there, you know? So if you fix this r right now, it's not moving anymore. You cannot fix your r until after the differentiation step. After the differentiation step, you're free to fix your r. Clear?
What's that? So above that?
So. All right, you want something more mathematical? We'll do the 3 dots, which means therefore. Therefore, that means therefore. So therefore, we have, I don't know, what is this? 72 pi? 72 pi. What? What are my units? Volume over time. Volume is measured in cubic units. And my units were feet, so cubic feet per second. So this sphere is growing. It's growing so that its radius is increasing at 2 feet per second. At exactly the moment that the volume of the sphere is 36 pi cubic feet, that means really that the radius was 3 feet, the volume is increasing at 72 pi cubic feet per second at exactly that instant. That's it. That's the answer. What do y'all think? All right, we still have a few minutes and I need to pass the sign-in sheet around. I'm going to show you just kind of a preview of some of the problems we're going to be doing. I'm going to say, there you go. So take a look at this. All right, here, I'm going to make one up. I'm not going to show you the one up here. I'm going to just make one up. Just to give you an idea of how messy this can be. Let's say that we have the ground. And let's say that we have over here a light. Okay, let's say this light is shining. Guys, we have a light, okay? And let's say this is a 40-foot pole, all right? You got this light here. And let's say that, I don't know, 30 feet away, you have a point on the ground. And you have this person who, I don't know how I want to do this. Let's say that you have a ball. This is a ball. And you drop this ball. Okay? So you start from 40 feet, all right? Same height as the pole, and you drop this ball. And it's going to come hit the ground eventually, right? What I would like to know is that at a specific moment, let's say at the exact moment that the ball is, let's say, 10 feet off the ground, I would like to know how fast its shadow is approaching the ball. So think about this. You have the light, right? Where's the shadow of this ball? It's going to be straight line. Shadow of that ball is on the ground over here, isn't it? But when the ball was up here, the shadow was way out here. Do y'all see that? So as the ball drops, the shadow starts coming in. And eventually, the shadow meets the ball. So at that exact moment, how fast is that shadow moving across the ground? That's a good question, right? That won't be on this test. That'll be more like on the next test, all right? But this gives you some idea of where we're headed. And since y'all liked that, we have, let me scroll down here to one of my favorites here. Where's, oh, there's a street light one. Okay. There we go. This one right here. Here we go. You have a cone that's being filled with water, and this water is being poured in at a constant rate. So I'm pouring this in at a constant rate. All right? Let's let it start over again. Notice in the beginning, it comes up very fast. Why? Because it's very narrow, right? So it's coming up very fast initially, and then if I'm pouring it in at a constant rate, it gets slower, doesn't it? At any point in time, I can say right there, how fast was it coming up the cup? How fast was the height changing? Understand that question? So we'll be looking at a lot of these things. And these, like I said, they become a little bit challenging. A runner runs around a track, and then somebody's sitting there watching them, stalking them, right? And so at any point in time, this runner's running at a constant rate around this track. At any point in time, I would like to know, like let's say right there, if they had a rope between the two of them, how fast is that rope coming out of this person's hand? So in other words, how fast is the distance between them changing? Now, this is like a crankshaft and like a piston. in an engine, you can start doing things like that. You have your crankshaft turning. How fast is the piston moving at a certain instant in time? There's a lot of different things you can do. But, you know. All right. Have a great weekend? Yes. Do your homework. Get caught up on 2.6. All right, let me turn my camera off. If you have that problem from last time, just put it up on my desk.